Okay, this video today is going to be basically for people who are absent. We're going to go through this in class, but if you are not in class, then here is the video of what we are doing. So let's look at example number one. First of all, let me back up. This is going to cover compound interest. So we've covered a little bit about interest and exponential growth, but compounding is actually more than what we've talked about so far. So compounding introduces a couple of new concepts. And so this video is going to go into what does it mean when we say compound interest. All right, the first example. If we have compounding interest and we're compounding it annually. So when you talk about compound interest, when is it that extra money is being added on? So we're talking about usually, not usually, but in the examples that we've done in the past, that has been added on at the end of the year. That was implied. So that's what this first example is. So let's go ahead and read through the example. A youth group has a yard sale to raise money for charity. The group earns $800 but decides to put the money in the bank for a while. Their local bank pays an interest rate of 3% per year, and the group decides to put all of the interest they can earn, that they earn back into the account to earn even more interest. So that's that compounding concept. All right, a couple things to remember. Remember that 3% is 0.03. Do you remember the equation that you would use to do that? So take a minute now to fill in this table. However you are going to do that, whether it's by adding every time or equation or whatever. So take a minute to do that. Pause here and see what you can come up with. All right, so the numbers in the table, this might be a little bit hard to read. The bottom one is $1,043.82. So if they put their money in at that, we call that year zero, then also in your table, look, I should have mentioned this before. I'm skipping between years 3 and 6 and then 6 to 9. So if your numbers are a little bit off, go back and look what you did. These first three should match up, but then if you were off, go back and look at your table and see if you can find these numbers that correspond to the 6th year and the 9th year. Because the equation I was using is y equals 800, that's our starting amount, times 1.03. 0.03 is our interest to the x power. That's a formula that we've known so far. That's not a new formula to us, but I'm going to use this example to move on to a couple other things. All right, so that's the formula. This is the table. How long until the money doubles? All right, there is an algebraic way to solve that. It involves logarithms. We haven't learned it yet. So instead, since we haven't learned it yet, what you need to do is just scroll down through your table and see where it is in your table. So do that. Scroll down, and when was it that the money was doubled? So we start with 800. When does it get to 1600? Okay, so you should see on your table that it's between years 23 and 24 where it doubles. Okay, that again, we have to scroll right now to do that. There is a way using logs. We just haven't learned it yet, but we're going to come back and figure out how to do that algebraically so we don't have to scroll all the way down. All right, so I was using that as an example to get us started. That example was compounded annually. This next one says, well, what if we compound it monthly? Well, we have to think about what that means. When the bank says they're paying you 3% annually, but they're compounding it monthly, they're not giving you 3% each month. What they're doing is they're taking that 3% annual number and dividing by 12. Okay, so what they're doing is they're taking that 3% annual and they're dividing by 12, and that comes out to be 0.0025 every month, or 0.25%. But we want to put it as a decimal so we can put it into our equation. So it's 0.0025 every month. Now, I will also say on this point, do not round these. Like if this came out to be 0.00333 repeating, do not round it to 0.33. If the bank rounded it to 0.33, they would get into big trouble because they'd be cheating you out of your money. So don't round it. We'll talk about what to do instead, okay? But don't round this. So 0.0025, that's 4 decimals, we can deal with that. All right, so now we're going to use that same formula we were using before, but we're going to modify it because we're talking about every month rather than every year. And so look at my table again. I'm measuring in months, and then I get to 1 year and 3 years. Well, 1 year isn't that 12 months, and 3 years is in that 36 months. Okay, so the formula that we're going to use, what would that formula be? It's going to be the same formula, but I might just call that exponent m to remind myself that I'm measuring it in months. So now I can put that into my calculator and I can look at my table and I can see what my balance is going to be. Okay, so if you look at what we have, $802 after the first month. Remember, it's not getting that full 3%. It's only getting 0.0025. So 802 after the first month, 806.02, 812.08. After a year, 824.33 cents, and after 3 years, $875.24. Let's just take a second to compare that to the table up above. And up here, after 1 year, it was $824. Here, after 1 year, it was $824.33 cents. Okay, after 3 years, here was $874.18. After 3 years here, $875.24. So you're getting a better deal when you're compounding it more frequently, but not a huge deal, right? I mean, it's just a couple of cents basically after 3 years. So it's really not a huge deal, but it is a little bit more money. But again, not a whole lot of money. Okay, so that is how we are going to do it if we compound it in a different time period. Instead of annually, if we go monthly, we're going to take that percent and divide by 12. And then we're going to use that same formula. Okay, we also have a new formula that we would use for this. And that formula, okay, so the formula A equals P times 1 plus R over N to the power of N times T. Let me tell you what all that means. A stands for your ending amount. P stands for your principal, and principal is just a synonym for the starting amount. R over N is the rate over the number of times compounded. And that's what we did up here. We took 3%, that was the rate, and we divided by how many times it's being compounded per year. 12 times because it was per month, so we divided by 12. So we took 0.03 divided by 12. That's what this is, 0.03 divided by 12. And then NT, honestly, this exponent, you can really use whatever you want. Let me tell you what I mean is, up here I used M to remind me that it was in months. So NT would be the total number of compounding periods. For example, in the example above, if I had 2 years, then I would have to put the power of 24 because that's how many times it was being compounded. So don't let that N times T of this exponent confuse you too much. Just if you think about it logically, I think it'll work out. I used M up here, so I knew it was months. I'm using N times T because that is 12 times 20, 12 times 2, so we've got 24 months altogether. All right, so this formula now is a new formula that we can use when we are compounding other than annually. So in other words, if we are compounding it monthly or weekly or daily, we can use this formula instead of the formula we had been using. It's just a little bit more complex. It has a little bit more in it because the concept is more complex. You're compounding it monthly or weekly or whatever. All right, let's turn the page. All right, on this page, for now, we're going to skip number 3. If you watched the number file video, which you were supposed to have watched, he went through this example on the scratch paper, talking about, if it's how many times it goes up and going up infinitely, and then you get to the E. But this next example, example 4, is going to continue on with that. And so the concept that I was talking about a second ago was continuously compounding. And so this is what he was talking about in that number file video. If you are compounding it continuously, in other words, not every year, not every month, not every week, not even every day, not even every second, but continuously, that rate is continuously turning over, then how much money will you have? And so over here I have a conjecture. That means like an educated guess. How much more will you have after 3 years as to compare to just compounding annually? So these numbers, it's the same table I had before. And so I took this table and I just recopied it here. So these are the numbers that you should have in your first table. I copied them here so that we can compare them. How much more do you think it's going to be if you're compounding continuously? Well, because this is a continuous compounding problem, the function that we're going to use is going to be very similar to one that we already know. That is, we're going to do y equals 800 as our starting amount. Now our rate, instead of saying 1 plus the rate, we're just going to say that that rate is E. And remember, E is a number that you're supposed to know, 2.718, and it's just a number is all it is. But it comes about through this formula of 1 plus 1 over n and all that. And so we're going to use that as our compounding rate. And then we still need the n times t over here, which is going to be 0.03 times t. And so it's a little bit different over here in the powers. Let me get that so you can read that better. All right, for now, let's use this. Let's plug this into our calculator. Your calculator has an E button on it. Let me show you where it is. Okay, on your calculator, do you see over here you have a couple of buttons? We have a log button and we have an ln button. And above the ln, we have an e to the x button. So if you type in shift and then ln, that's e to the x. So we have e to the power. The power is already set up for us. So now we can put in that power 0.03 to the t. Let's go to the y equals button and let's just go ahead and plug this in. I'm going to clear out my old equation from yesterday and I'm going to plug in 800 times e, so this is where I'm going to use this button here, to the power of 0.03t. And we just use the x button, just use the x. It has a t actually on it, but we're using the x. That's all we need. Don't worry about the other variables, let's just use x. All right, so now we have that equation, and so now we can do a table with that. And so we get our table. So now take a minute now to copy those values onto your paper. Okay, so we fill these in. Let's take a second and look and compare them. All of these numbers are a little bit bigger, but just not a huge amount. If you've put in $800 and after 9 years you have $143.80 more, or you have $147, so you're getting $3 more this way, which is money. I mean, you can't discount that. It is money. And if you were, putting in $1 million, it'd be a lot of money. But it's just percentage-wise not a whole lot different. And so banks will typically use the E because it's just as easy for them as it is to do it a different way, maybe even easier to do it this way. And that way they don't have to worry about, when you take out your money, are you going to prorate it, whatever. It's just really simple. And so it's a simple equation. It's a simple way for them to do it. And you, as the consumer, you're getting a little bit more money, but really not a whole lot. And so that's one of the takeaways from this. Now, how long will it take the money to double? Once again, we have a way to do that in algebra, but we haven't learned it yet. So let's just go to our table, scroll down through your table, and see when is that $800 going to become $1,600. Okay, did you see it coming between 23 and 24 years? And if we look at the previous page, that's the same thing we had on the other page, between years 23 and 24. And on this page, we've got between 23 and 24. Same amount of time to double our money. All right, but we do have a special formula. You do need to know it, and in other words, memorize it. And so the formula is A equals capital P times e to the RT. And the good thing is this makes a little mnemonic, PERT. So we call this the PERT formula. And PERT, the A is the ending amount, just like it was on the other page. The P is the principal, the starting amount. Again, same thing like it was on the other page. The E is the E, the 2.718 that we're learning about. And then R is your rate and T is your time. And so that's where this formula came from. You didn't know it a second ago, but this is the PERT formula. The principal starting amount, E, to the power of the rate times the time. That's what that is. So we need to know this formula because we will be using it quite frequently. And it's a kind of a famous formula. It's one that comes up frequently. Okay, what are some of our big takeaways from this lesson? Well, one thing is when compared with linear growth, exponential growth does what? So what are some things that we've talked about? Write down something that we've talked about, how those two compare. Okay, whatever you wrote down there, I wrote down it might start off slowly, but eventually it really takes off. So remember that we talked about in class the other day, the linear might go like this, the exponential might take off, might start more slowly, but then it really jumps up and really exceeds the linear by quite a bit. And then how about the number of the times the principal is compounded? If we compound it annually versus monthly versus daily versus continuously, how does that affect our ending amount? Okay, what did you write down? I said the ending amount is a little bit higher, but not much. So it does make it a better deal for you, the consumer, but it just isn't that much percentage-wise. If you're talking about getting a better deal, probably your percent interest is more important than how frequently is being compounded. Those are the notes that we went over in class on Wednesday and Thursday. So we did some examples like this, and then we did all the book problems that are out of the Big Ideas book on pages 300 and 307. So those are the ones that you'll do at this point.